Welcome to the third lecture of week 1, which is on stress-strain relationship. Discussion on stress and strain relationship we have started from lecture 2, where we have defined stress and strain separately and discussed types of each, and then we have derived expression for biaxial as well as triaxial system. So, in this lecture we will solve example related to stress and strain relationship, and then we will discuss a few more stresses. So, let us start this. And here I am having example 1, and it states that stresses are to be determined at the inside corner of an opening in a cylindrical shell by applying strain gauge at the location. So, in this problem a cylindrical shell is considered where an opening is made, and due to this opening whatever strains are generated, that are measured through strain gauge, which is the instrument to find out the strain at a particular location. And cylindrical shell is made of carbon steel with E value 20 into 10 to the power 9 Newton per meter square and mu is 0.3. The strain reading from the 3 gauges are epsilon x, epsilon y and epsilon z as mentioned here. What we need to compute is the stresses in the 3 direction at the opening, and second part focuses on stresses in 2 direction of the cylindrical shell where sigma z will be equal to 0. So, these 2 parts we will solve for example 1. So, let us start with part A. So, in this part we have to calculate stress in 3 direction at the opening, and if you see here we have epsilon x, epsilon y and epsilon z. So, opening whatever we have discussed, that is basically of rectangular type, and we need to find out stresses considering values of strain, and relation between strain and stress are already derived in lecture 2 for triaxial system. And what are the known values? E and mu are known values along with strains in all 3 direction. So, that example is not very much complicated, that is very simple. We have epsilon x, epsilon y and epsilon z expressions where I know E and I know mu. So, putting the value of epsilon, E and mu, we can have the equation in terms of sigma x, sigma y and sigma z, and these are 3 equations where sigma x, y and z all 3 are unknown. So, we have 3 equations and 3 unknown, so that can be solved simultaneously. Once we solve that simultaneously, we can obtain the value of stresses in 3 direction, and sigma x here is 1.158 in 10 to the power 7 Newton per meter square. Sigma y and sigma z contain these values respectively. So, in this way we solve the stresses generated in 3 direction when I know the strain value, and if I know the stress values I can calculate strain in all 3 directions. Okay. So, that is the part 1. In second part we need to find out stresses in 2 direction of cylindrical shell where sigma z is equal to 0. So, here I am having the relation of sigma x as well as sigma y as a function of epsilon x and epsilon y. This is biaxial system, these equations we have already derived, and while putting the value of strain E and mu, we can have sigma x as well as sigma y. Okay. So, sigma x it is simply the expression based, not complicated solution is required for that. So, sigma x comes out as 1.077 into 10 to the power 7 Newton per meter square, and sigma y we can obtain as 0.923 into 10 to the power 7. So, these values are directly formula based, where stress if no we can calculate strain and vice versa also. So, this is the simple example to compute stress whatever we have discussed for biaxial as well as triaxial system. Next we have the materials of construction, that is the mechanical properties. Now what happens, you have seen that stress and strain relationship and that vary for each material. You cannot have that 2 material have same trend, no, it is different. Now why it is different? Because each material will have different crystalline structure, either it is very simple or it is complicated, or there may be different size of molecules available in that, and their geometries are different, geometry of molecules are different. So, the crystalline structure of material vary, okay, material to material, and so based on that we can define some properties, and we call these properties as mechanical properties. And in this slide we are focusing on some of the important mechanical property. The first property is the strength. So, strength represents the capacity of the material to withstand external forces. Okay. So, that when external forces are applied to an object, it will try to deform it. Okay. So, external forces should be resisted by the object. So, strength is defined in that way, so that up to what extent it can resist the external forces or deformation. Okay. So, depending upon the nature of force, strength can be classified as tensile, compressive, shear and impact. Okay. So, basically strength speaks about that how much a particular material resist the force which are acting on this. So, strength can be defined that for how long the material can withstand the external forces or can resist the external forces, so that it should not be deformed. Okay. So, this is one property. Second property is stiffening and rigidity. It is a measure of the ability of the material to resist deformation, and modulus of rigidity is used to express this property. And next I am having elasticity. Elasticity, you understand that when we apply stress to a particular object, it deforms. When we remove that load or stress, that the material will regain its original, the material will regain its original shape. So, that we can call as elasticity of the material. So, in the design of most of the component, permanent deformation are generally avoided and material is utilized with the view to retaining its elasticity. So, while designing we usually avoid permanent deformation, because until unless it will be in elastic region, if any deformability will appear, it will regain its original shape. Okay. So, which is not possible in and that is not possible in permanent failure. So, elasticity is a important property, as it determine that up to what extent we can consider the values, we can consider the parameters while designing. Another property is the ductility, which is a measure of deformability of the material, determined by percentage of elongation or reduction of area. What is the meaning of deformability of the material? For example, if I am having this wire, okay, and if I pull this wire from this side, okay, if I pull this wire from this side, up to how long it will retain its shape, though deformation will take place, but it will remain as a wire. Okay, up to how long it can maintain its shape without breaking. Okay. So, as much as length can be increased before breaking of this wire. So, that increment in length basically speaks about the ductility of the material. Next property is the toughness. It is the ability of the material to absorb energy in deformation in the plastic range, and is measured by finding out the total area of stress strain curve. So, this is basically the toughness, where how much energy is absorbed in deformation, that quantifies. Okay. So, next property I am having is the hardness, and hardness basically speaks about the surface characteristic of the material. It means it when the material will be very hard, it will resist the scratching. Okay, scratch are not formed very easily on the very hard material surface. Okay, so it is basically the surface characteristic. And then we have the creep. It is a slow and progressive deformation of a material with time under constant stress. So, you see, in this way we have defined different properties, different mechanical properties of the material, and now we will focus on those properties which we usually use in designing, okay, and that we can derive through stress and strain relationship. So, first property in that case is the proportional limit. Now, if you consider this particular diagram, here we have stress on y axis and strain on x axis, and here we have trend of a particular material. So, point A on this diagram indicates the greatest stress up to which Hooke's law of proportionality of stress of strain is observed. It means this is almost a linear part of a material. Okay. So, where this linearity disappear, we call that point as the proportional limit, because up to proportional limit it follows the Hooke's law. Okay. So, that point A is basically the extent of linearity, you can understand. Okay. So, this is one property. Another property is the elastic limit. Elastic limit, you see. So, this is basically the maximum stress beyond which permanent deformation will take place, as it is shown through point B. So, without having permanent deformation, how much stress can be sustained by the material, that is represented by elastic limit, and that is very close to the proportional limit. Next, we have the yield stress. It is the stress at which the resistance of the molecules of the material begins to break down rapidly and sudden large increase in strain occurs without increase in stress. Okay. So, that is denoted by point C in this image. So, what happens if you see stress at point B as well as point C, stress is almost uniform from B to C. Okay. However, strain has significant change. So, the point where sudden change in strain occur without having much change in stress, that point we can call as the yield stress. Okay. And after we have ultimate stress. Ultimate stress is basically, it is the greatest stress at which failure of the material takes place. Okay. So, if you consider this point D, that we denote as ultimate stress, and from C to D we consider the region as plastic region. Okay. So, here from C to D we have permanent deformation, and D point is basically the maximum stress at which failure of the material take place permanently, and this is the region from C to D where Hooke's law will not be applicable. So, these are some of the properties which we will consider in designing. At what level we will consider, that we will discuss when time comes. Now, next topic in this series is the membrane stress. Here we have we will define what is membrane stress and how these how the expression related to these stress can be derived for a given system. So, for the purpose of design and analysis, pressure vessels are to be subdivided into two classes depending upon the ratio of thickness to vessel diameter. So, ratio of wall thickness to diameter speaks about the class of pressure vessel. Okay. So, when this wall thickness divided by diameter, if it is less than 0.1, it comes under thin walled vessel, otherwise it will be called as thick walled vessel. Okay. So, when the ratio of thickness of the wall to diameter is 0.1, whatever stresses are generated in the metal sheet or in the component which we are going to design, that stress is basically called as membrane stress, because that is very thin layer and it will be treated as the wall of the balloon. Okay. and here we will derive the expression of membrane stresses on cylindrical shell. So, here I am considering cylindrical shell where the length of the cylindrical shell is L and inside diameter is given as di, okay, and T is the thickness, of this, you see this is basically T, thickness of metal sheet by which this cylindrical shell is prepared, okay, and this system is operated with internal pressure. So, when the system is operated with internal pressure, it means internal pressure will be higher than the outside pressure. Outside pressure should be maybe atmospheric, inside it will be more than atmospheric. So, once it will be more than atmospheric, it will try to expand it from internal, okay, and then we can have the failure if we will not go for a proper designing of that vessel, okay. So, when internal pressure will act, it has certain stresses or some stresses which are formed, and these stresses are usually available along the length and around the circumference, okay. Because of internal pressure operation, we have two stresses, one is called hoop stress and second is longitudinal stress in axial direction, okay. So, to derive the expression that how we need to calculate thickness of that, we will make the force balances around the object, but before force balances you should understand what are the stresses. As I have told that there are two stresses, hoop stress as well as longitudinal stress. So, longitudinal stress, how that longitudinal stress will be formed, because if you see this image, L is the total length, from this side it is entirely covered and from this side also vessel is closed. So, whatever pressure are acting over here, that pressure would be try to expand these walls, okay, and try to expand this expand or we can say try to push this head or this closure, okay. So, once it will push this closer, what happens, it create stress in longitudinal direction, okay, because it will try to open those two ends. So, due to this whatever stress are formed, that we can call as longitudinal stress, okay. And what is hoop stress? Hoop stress is when internal pressure is acting inside, it will try to expand the diameter, it will try to increase the diameter because continuously it pushes. So, that you can understand through this diagram that all pressures pressure will try to expand this periphery from inside, okay. So, what happens when it will expand, it will create stress at this direction, okay, and when it will give and when pressure is applicable to this, it will give stress in this direction. It means this is basically the circumferential stress. If circular shape I am considering, it will try to the pressure will act upward as well as downward. So, it will try to expand this. It whenever failure will occur, it will try to it will be failed from in this side. So, all these stresses will cause circumferential stresses, or which, so all these stresses will create circumferential stress, and we also call this as tangential stress as well as hoop stress, okay. I hope you have understood what is hoop stress, that is basically the circumferential stress, okay. So, for design purpose I need to make the force balances in this object. So, let us start with the circumferential stress or hoop stress or tangential stress. Now, what happens over here, whatever stress hoop stress I am telling, that is basically sigma 1 here as well as sigma 1 here in this diagram, okay. So, this sigma 1 will be generated due to force F, which is applicable to this direction only. So, that force is basically balanced by all vertical component of this up to this section, Okay. Vertical component of all forces which are acting in this region will be balanced by F. In the similar line, whatever F is there, that will balance all component of these forces in upward direction. Okay. So, to make the balance, if you see here I am taking 2F. Why I am taking 2F? Because I am making the balance in half of this image. Okay. So, F is there and F is there, so that would be 2F. How it is balanced? Like 2F equal to 2 integrating from 0 to pi by 2, integrating from 0 to pi by 2, and if you see here, if I am considering this particular section where this angle I have taken as theta. Okay. So, acting area of pressure in this region would be this distance into length in this way. Okay. So, this distance into length, how I can define this length? That would be di by 2 sin theta. So, how we can define this distance? That is r sin theta. R is basically di by 2 into sin theta, and when I am integrating this expression from 0 to pi by 2, it will give all forces in this particular section. So, here you see that 2 P is the internal pressure, L into this would be the acting area for a small angle theta, and that will be integrated using d theta. When I resolve this expression, I can have P, L and di. So, from this I can extract F as PLI by 2. Okay. Now, the hoop stress in shell can be obtained as sigma 1 equal to F by A. Sigma 1 you see here, and that is basically F by A. A is what? A is this acting area. I hope you are getting it. So, A is basically this acting area, and that is T is the thickness of that sheet along the length. That would be the acting area. So, here we have sigma 1 as PLDI by 2TL, and that will be PDI by 2T. So, sigma 1 will be equal to PDI by 2T. This is the final expression of hoop stress. Okay. And these expressions are valid for thin walled vessel where T by Di is less than 0.1. So, here this is this expression we have derived considering hoop stress in thin vessel. And usually if I am considering thick vessel, there we have radial stress also. Here we have only considered circumferential as well as longitudinal, and we have not considered radial, because in thin cylinder along the radius stress will not vary significantly. However, if I am having significant thick cylinder, inner surface to outer surface continuous change in stress is observed, and that we call as the radial stress, and that we will discuss when we derive the expression for thick cylinder. Okay. Now, another expression I am having considering longitudinal stress, that is sigma 2, and here sigma 2 basically represents longitudinal stress, and that would be balanced by the force which are acting on the cylinder in longitudinal direction. Okay. So, if you consider this particular image, here we have sigma 2. Sigma 2 will be applicable in this region. Okay. In this whole region sigma 2 will act. So, that sigma 2 would be what? That pressure into acting area. Acting area will be this area. So, how I can define that? Pi d into T. What is d? D is basically the average diameter here, and that we can write as di plus T, or if outer diameter is known, that should be d naught minus T. So, pi d is basically the periphery into T, that would be the acting area. So, pi dt sigma 2 will be equal to pi di square by 4 into P. P is the internal pressure which is acting on whole cross sectional area of the vessel, because it is acting in whole this area. So, that would be pi di square by 4. After resolving this, we can have expression of sigma 2 as P di square by 4 T d. where d is di plus t as I have already explained, and this is again valid for thin cylinder where t by d naught is less than 0.1. So, in this way we have derived the expression for hoop stress as well as longitudinal stress, and based on this let us solve one example so that it will be more clear. So, here I am having example 2 where a thin cylindrical shell having 3 meter inner diameter and 12 meter length is being operated at 3 mega Newton per meter square G. What is this G? G is nothing but the gauge. So, pressure is given in gauge. So, why I am considering pressure in gauge, that we will discuss later on. What we need to compute is the thickness of shell if allowable stress of the material is 200 mega Newton per meter square. So, what is allowable stress, that again we will have a separate lecture to define this, and there we will discuss when time comes. Please consider this allowable stress right now as it is. Okay. So, let us start the solution. Here I am having di and length, and internal pressure is given 3 mega Newton per meter square, and allowable stress we have equated to sigma value, either sigma 1 or sigma 2, whatever expression I am using. In that expression sigma will be replaced by allowable stress. How it is replaced by allowable stress, that also will be discussed in upcoming lectures. So, sigma 1 and sigma 2 expressions, these expression we have already defined. Considering sigma 1, we can calculate T as 1.05 into 3 into 3 divided by 2 into sigma 1 will come over here once I take T from this expression. Now, what you need to focus on, what is this 1.05? See, when I am operating the vessel at a particular pressure, usually I design a value higher than this, or we can call that as over design, because failure should not occur. Therefore, the pressure we are, whatever pressure we are considering, that should be slightly higher than the pressure at which I need to operate, and usually that value we take as 5% extra. So, 1.05 into 3 resembling to design pressure. So, after solving this we can have thickness 23.6 mm. Considering longitudinal stress, we can calculate thickness as T equal to 1.05. Why it is, that we have already discussed, and then 3 into 3 into 3 divided by 4, 200, because sigma 2 will come at the bottom, into D plus T. So, here you see T is coming here also as well as here also. So, that you need to solve it properly, and the final answer would be 11.77 mm. So, among this, as this would be of higher thickness, we can consider this 23.6 mm as final thickness. So, in this way we can solve the problem, or we can design the system considering membrane stresses, and which are applicable for T by D naught is equal to less than 0.1. For higher thickness, we will derive the expression separately, and that will come under thick walled vessel. And here I am having some reference books which you can follow to study the topic in detail. Now, we have the summary of the video, and this summary is combinedly written for lecture 2 as well as lecture 3, and here stress and strain are defined along with types of each. Poisson's ratio of a material is defined. Stress strain relationship for biaxial as well as triaxial system are discussed, and mechanical properties of material are discussed. Membrane stresses are defined, and expression of membrane stresses for cylindrical shell are derived. So, I hope you have idea how to compute the thickness for membrane stresses, how to derive the expression for stress strain relationship for a given system, and that is all for now. Thank you.